Like I said yesterday, if you saw the email, the average on the test actually improved, pretty well. A lot of people made some, in fact, a number of people made some pretty good improvements, so that's good. Make sure you know what you did wrong on the test, right? Go over it, try to figure it out. And if you can't get it figured out, come see me. That's what I'm for. Also, between exam 3 and the final, I'm gonna do another one of these. Come to my office and you get like a 3 extra hundred on the quiz. Make sure you take advantage of that. So, and I will, after class, be posting sometime this afternoon, next quiz. Anybody ever come across this before? Eigenvalues, eigenvectors, differential equations?
No, just in the world of math.
In the world map, right? If you've had, how many of you've had differential equations? Anybody? Did you ever talk about eigenvalues? Right? You might have talked about these in systems of, in solutions to systems of differential equations. So if you haven't had differential equations, it'll come up then. What are the simplest types of linear transformations? Well, that's an opinion question, so that's right. Take every vector and number, multiply by some number. That's the easiest type of linear transformation I can think of, right? In fact, I really like it if A is 1 or even 0, right? That's a very simple type of linear transformation. The idea behind eigenvectors and eigenvalues is you look at a general linear transformation and you try to pull out the places in the vectors where it behaves like this. And I'll give you an example of this in a moment, but can anybody think of an example? So the easiest linear transformation is TV equals AB. So for example, if I do this in the plane, this takes any vector and just doubles its length. Right, so basically, I'm stretching the entire plane out in every direction, just stretching it out from there. Agree with that? Every vector has this property. Can anybody think of a linear transformation, say from R2 to R2, where there is no vector whose output is a multiple of that vector, other than the 0 vector? Here's a linear transformation plane. Just twist it. Everything clockwise or counterclockwise 45 degrees. So this vector goes maybe to this. Is there any vector in the plane other than 0 vector that output is a multiple of that vector itself? No, it's always turned. Everybody agree? Every vector, there's no vector that is a multiple of itself under this linear transformation where I just turn the plane. I agree. How about 3-dimensional space? You might think of a linear transformation in 3-dimensional space where no vector is a multiple of that vector. Somebody describe how it can be done. That's an idea, right? So maybe if you turn, so imagine it, instead of doing like a little wheel there, I do a globe, right? Shouldn't I be able to turn a vector this way and then maybe this way, and so no vector is multiple itself? I would think that's good, but it's impossible. You cannot, it cannot be done. All right. We'll go to that in a moment. Let me give you a definition here. Um. Let's let A be n by n matrix. And again, this is just like invertible matrices. When I'm talking about eigenvalues and eigenvectors, I'm talking about square matrices here. An eigenvector for A is a non-zero vector B such that A, B equals lambda or some lambda, some number. So an eigenvector is just a vector that's acted on very nicely by this matrix, right? This might be a very complicated matrix, but for this special vector, all the matrix really does is stretch it. Or if this is negative, maybe turn it around 180 degrees. But basically, this vector is still in the same line that it determines in space, whatever dimension space. Okay. What is an eigenvalue? It's basically the lambda. So lambda in R is an eigenvalue if there is a non-zero vector B such that A, B equals lambda. Sometimes we call this so I'll use this terminology sometimes. If A, B is equal to lambda B, sometimes say lambda B is an eigenvector. Okay. Let's look at this using, shall we? I'm gonna do some 2x2 ones that kind of gets warmed up. Let me point something out, and this one's kind of easy just to figure out. I agree with that. This linear transformation, I mean, this matrix, it's all fancy, and I feel very important about myself, but the matrix is actually just multiplication by 3, right? That's essentially it, right? And notice that any vector is an eigenvector or eigenvalue of A, B is 3B. Am I okay with it? Okay. Let's generalize this. Let's generalize this a little bit. Now let A equal 4, 0, 0. Anybody spot a vector that is just scaled? multiply the vector, if I do this matrix to it, it'll just multiply the vector by 4.
One, two.
Oh, I agree.
Yeah.
Because this gives 4. Okay. So. There's an eigenvalue, eigenvector there. I don't know why I wrote that minus, definitely a plus. Right. And can anybody rip off another one? What's another eigenvalue, eigenvector there?
Negative.
Okay. I agree with that. So I get another one. There's another eigenvalue. Now, here's one with a little more meat on it. Seven. Seven minus 15 and 2 minus 4. Let's spot an eigenvalue, eigenvector pairs. Looking at that. You're a daisy if you do. This one's harder to see. I'm gonna use some magic prestidigitation and just notice that 2 let me just verify that it works. I'm just gonna verify that this is an eigenvalue, eigenvector pair. Well, let's see. If I look at 7, 2 minus 15 minus 4 comes the vector 2, 5. Let me see what this becomes. This becomes 14 and 10 is 24. Right? And this becomes minus 30 minus 20. So that's going to be minus 50. Actually, something wrong here. Oh, no wonder. Things down wrong. Negative 5. Let's try that again. That's 14 minus 4. Because this is going to be 14. Oh, no, it's not 14 minus 10 plus 4. And this is going to be minus 30 plus 20 is minus 10. Can you tell me now what the eigenvalue is? Yeah, that's right, because basically I've just taken my vector and I've stretched that to 5. So this is 2. Now, the first thing that you may complain about is, well, that's great. Where did you get the eigenvector, right? I mean, I just pull that one out of thin air. And at this point, I would have to admit that it's correct. I'm going to show you how to do that, though. Let me pull an eigenvalue and see if you can tell the eigenvectors. As it turns out, another eigenvalue is 1. How can we figure out what the eigenvector is? Well, let's just have a little faith in me for now, and let's assume that I'm correct about this. So what I have is A, B is equal to 1 times B, right? So this means that AB minus B is equal to 0 vector, right? Now I'm going to pull out a B here. B minus 1? A minus C, I didn't, right? Because it says else, it says 2 by 2, I think. Okay. Now, this matrix, for this to have an eigenvector, remember, this has to have a non-trivial solution. So for some B not 0. Everybody okay with that? And if B is not 0, this is a solution, a non-trivial solution to this homogeneous system, right? So what does that mean about the determinant of this? The determinant must be 0 if it's got a non-trivial solution. So to find the eigenvector, we need to find non-trivial solution or solution to well, what is A minus I? It is 7, 2 minus 15 minus 4 minus 1, 0, 0, 1. Right? Which I guess comes to 6, 2 minus 15 minus 5. We just need to do the row reduction and find the homogeneous solutions to this, right? And then we'll check if this works. So, what do we got here? 15 minus 5, and we want to go to the row reduced echelon form because really, again, see how these concepts all kind of repeat themselves. What are we doing? We're finding a null space. Is what we're doing again, right? For the like zillionth time. What can you say about the 2 rows?
They're nearly.
That's right, because actually this row is negative 2.5 times 30, right? So this is actually equivalent to, I can use this row to take this one out, and then I'll multiply this or divide this by 3. Actually, I did say row reduced echelon form, didn't I? How about that? Everybody okay with that? This is an easy homogeneous solution to solve. I have x1 plus 1/3 x2 is equal to 0. So my basic variable is x1 and my free variable is x2. So I should have the dimension of my null space should be 1, because it's 1 free variable. And I get x1 is minus 1/3 x2. So if I wrote the solution down this way, it would be x2 and minus 1/3 x2. So x2 times minus 1/3 1. Right? Or I can write this way. Minus 1/3, right? So basically, all I have to do is multiply top and bottom by 3 and call this x2 half, right? Let's check. This should be an eigenvector for the eigenvalue 1. Let's look at the original matrix. 7 minus 15 2 minus 4 times the vector minus 1, 3. This becomes minus 7 plus 6 is minus 1, plus 15 minus 12 is 3. There you go, that's the same section. So this is a complicated matrix. However, any vector that is parallel to this will basically just be barfed back out by this matrix. Everybody okay with that? So what we've seen so far is what an eigenvector and an eigenvalue are. I've shown how to test if it really works. I've even shown you sort of if you've got an eigenvalue, how to get an eigenvector, because you basically just do some null space problem. The big question is how do you find freaking eigenvalues, right? Well, I'm going to go back to this equation right here. This is important. I'm going to kind of write something a little bit more general up here. Actually, in this section in the book, they don't really tell you how to find eigenvalues, which is just but stupid. So I'm going to do it for you right here, so that you already know how to do it. So if you have A, B is equal to lambda, B and B is not 0, this gives A minus lambda I, B is equal to 0. This has non-trivial solution. That is to say, you get an interesting non-zero eigenvalue or eigenvector if and only if determinant of A minus lambda I is 0. This messy matrix here has to have 0 determinant to give you an interesting solution. So this tells me where to hunt looking for eigenvalues. So, example. Let's find the eigenvalues of this. I'm going to do this out longhand once, then I'll kind of shortcut it in futures. Of course, this is for the 2x2 case. If you were in the 3x3 case, it would be a bigger matrix and 3 lambdas down the diagonal. So this is the matrix when you put it all together: 7 minus lambda, 2 minus 15 minus 4 minus lambda. And you want this determinant to be 0. So check it out. So let's multiply this out. We know how to do a determinant. This is lambda squared minus 7 lambda plus 4 lambda is 3 lambda minus 28 plus 30. Everybody okay with that? Let's see what I did do. So this becomes they're your eigenvalues. You have it earlier. Namely in this case, 1 and 2. Um. Let's do. Actually, let me give you this, theorem first. We'll get a square matrix, and lambda is an eigenvalue of A. The collection of all B in Rn with AB equals lambda B. So all the eigenvectors that correspond to this eigenvalue forms a subspace. Let me give you kind of a quick proof of this. Subspace, what's the first thing you gotta have in a subspace? Zero vector. Does this work? A times zero vector is lambda times zero vector. Yay, right? Okay, so zero's in there. 2, if AB equals lambda B and AW equals lambda W, then A of B plus W is AB plus AW lambda B plus lambda W equals lambda B plus W. So notice that B plus W is also an eigenvector for the lambda. And finally, if you have A CV, this is lambda CV, which is right, lambda. So CV is also an eigenvector for the eigenvalue lambda. Okay. Any questions?
Yeah. So this is neat, but is there any particular reason why we're only getting like scaling vectors and not like other types of vectors?
Like what?
Well, let's say you had like your rotated example. Is there like an eigenvector thing where it rotates by 45 degrees or something? I mean, I guess it seems to me kind of arbitrary to like pick a scaling one.
Because actually, the scaling is the most important piece of linear transformation. Yes, you can break up the rotation. That brings me back to a question here. By the way, here's a quick. I'm totally not having a stroke here. But here's what you might need this in the future when you're finding polynomials of, say, 3x3 matrices. You get cubic equations for your eigenvalue. Can somebody give me any solutions to that? I don't know either. Does anybody see an obvious solution? Something an easy something you can plug in and solve. But I agree that 1 is a solution to this. You plug in 1, it works. if you can find one solution to a cubic, you can find them all. How?
You factor out the solution.
That's right. This is a solution one. Is everybody clear on that? That means, I promise you, that this thing has a factor of x minus. So all you gotta do now, play Dick Tracy and figure out what the rest of it is. It should be x squared, and that should, square term should cancel, and it should be that. Always. This gives you the solution one, and the quadratic formula will finish you off. By the way, how many solutions does this one have? Let me rephrase. How many real solutions does this have? That's zero. Right, y'all remember the quadratic formula? Right, yeah. Brush up on that. The crap that goes under the radical is this squared minus 4 times this times this. What goes under the radical is negative, so there's no real solutions to this. We'll get to, actually, the complex solutions, the complex conjugate solutions, they tell you something about the rotations. Don't get that to it for that later.
Is it negative or is it one a solution?
Huh?
Isn't one a solution?
One is a solution.
Okay.
And there are two other solutions, but they are complex conjugate. Everybody okay? But, so remember that. This is true for any polynomial. If you ever see something easy that you can plug it in and you get zero, that means it's got a factor of x minus whatever you plugged in. And then you can kind of reduce it down. Okay, so let's look. Everybody agree, this is the identity thing. This is almost a silly example because this takes every vector and just leaves it alone. So every vector is an eigenvector with eigenvalue 1. So the eigenspace has dimension 2, right? Because the eigenspace is all of R2. Agree? What about this one? Let's figure out the eigenvalues for this, shall we? If I agree. By the way, the polynomial you get by taking this determinant is often called the characteristic polynomial. In this case, you get 1 minus lambda squared, right? Minus 0, right? Would everybody agree that you get the same characteristic polynomial for both of these? In both cases, you'll get 1 minus lambda squared, right? Because the other term doesn't matter. You get a 0 here, and you get a 0 here. Everybody with me on that? So this sort of at first gives you the same data. But it's not true that every vector, so if you've got one eigenvalue, 1. But it can't be the case that every vector is an eigenvector because this isn't the identity matrix. Yes.
So is the identity matrix the only matrix where every vector is going to be the eigenvalue for that, or the eigenvector for that?
No, any scalar matrix will work. So if I had the matrix, if I had 2 times the identity, that'll still be true what you said. So your eigenvalue is 1 here. Well, let's find the null space. Well, so a minus lambda x here, lambda is 1. So when I plug in my eigenvalue here, I get 0, 1, 0, 0, right? Now I've got to take that to row reduced echelon form. Yay, I'm already there, all right? There is, oh, we need to interpret this, I guess. There's only, what, there's one, there's one pivot. And so this means that, what does it mean? It means x2 is 0. That's your basic variable. And there's no equation governing x1. X1 can be any. So your eigenvector looks like this. In this case, the eigenspace, all vectors are eigenvectors. So the eigenspace for the eigenvalue 1 has dimension 2. Because it's all of R2. Over here, the eigenspace for lambda 1 has dimension 1. Because there's only one free variable. Yes.
So just to clarify, the eigenvector for a given eigenvalue is the null vectors.
Yes,
Vectors
so,
of that eigenvalue is
Suppose you've got your eigenvalue lambda, a minus lambda I, that make that matrix.
Right.
Now find the solution, the null space for that. That's what you're looking.
And what if there's more than one null vector?
Oh, there certainly can be, like in this case right here.
Right. And then both of them are eigenvectors for that value.
That's right. This eigenspace. So the eigenspace for an eigenvector, I'm sorry, for an eigenvalue, the eigenspace are all the eigenvectors that work with it, right? And here it's two-dimensional, right? It's 1, 0, 0, 1, everything works. Let's look at another example here. So let me, actually, I think I'm going to put your also notes here. So let me just be clear here. Definition. If lambda is an eigenvalue for A, then set of all vectors such that it's called the eigenspace. The eigenspace of A corresponds. So it's just all the eigenvectors that work with that. Okay. I've got a couple more theorems to cover and maybe these examples. Now that I've taught you how to do this, I think that your book puts this in this section for some puzzling reason, but now it's easier. I've told you how to do this. Here. Yeah. A is a triangular matrix. It can be upper or lower triangular. I'm gonna write it's upper. Can also be a lower triangular matrix as well. Then the eigenvalues. Are. Anybody want to guess? Diagonals. That is correct. So in this case, by the way, what is the relationship between the eigenvalues and the determinant of that matrix?
Determinant is the product of all the eigenvalues.
Yes, and this is actually true in general. If the matrix has, it's actually even true. If the matrix only has complex eigenvalues, and I'll show you that as well. Let me prove this for you. I'll do this in the upper triangle case. The eigenvalues, now be careful, folks, this only works for an upper triangular matrix. So define eigenvalues. With the determinant of A minus lambda IN. So that matrix would be A11 minus lambda, A12, 3, A1N, 0, A22 minus lambda, A23, A2N, 0, 0, A33 minus lambda, A3N, blah. A, minus lambda. Well, I'll take the determinant of this. Now notice this matrix is still upper triangular, right? How do you take the determinant of an upper triangular matrix?
Just the diagonal.
Just you multiply the diagonal elements. So the determinant of this is equal to A11 minus lambda, A22 minus lambda, A n minus lambda. And so it's pretty easy to see, isn't it, that the roots of this are yes.
Quick question, if we have like a determinant, like, let's just say they have like 28 or something, if we took the greatest common factors of that number, is that the eigenvalues or is that not the same range?
So give the determinant what number?
Like just like some number, if you break it down to its smallest components, would those be the eigenvalue? Or no?
I don't know what you mean by breaking it down to the smallest components though.
Like its greatest common factor.
Yeah, but you're talking about probably the integers, right? And in general, I expect these to be real numbers like pi over square root of 2 and various things. And then you're gonna have all kinds of problems. Actually, when some people do linear algebra over just like the integers, there's actually a lot of interesting math that comes on there. That's, you can't really do that in this course. So. Okay, other questions? Let me give you one more theorem. Okay, B one, B two, B K are eigenvectors of A corresponding to distinct. That's very important. Eigenvalues. Lambda one, lambda two, lambda K. Then a set of vectors B one, B two, B K are linearly I'm not gonna prove this today. Your book does approve. It's fairly simple. But this is actually kind of an important theorem. If you have two different eigenvalues for a matrix A, and you pick an eigenvector for each of those eigenvalues, and those two are linearly independent, and that works for any side of the vector. All right, so this is kind of important. Yeah. We do another example here. It's not an eigenvalue. Okay. This is the determinant. 2 minus lambda, 0, 0, 0 minus lambda, 3, 0 minus 3, minus 1. Is that right? So this is 2 minus lambda times this little determinant here, which is going to be lambda squared plus 9. And then everything else is 0, right? Everybody agree? So you guys expect this and tell me what are the eigenvalues?
Two. Yeah.
And we're going to deal with complex eigenvalues later, but there's only one real eigenvalue. If I agree, the other two are plus or minus 3i. Everybody okay? Let's see what the eigenvector is for the one real eigenvalue. Or eigenvector. So we want the null space of, well, that's convenient. And already I see there's a non-trivial solution. Right, so I'm going to put the zeros on the bottom. I'm going to put this on the top, and I'm going to turn 0, 1 minus 3 halves. 0, 1 2/3. Right, so I just scale that down by -2, and that's scale that by 1/3, and this reduces to 0, 1 minus 3 halves. Multiply this by -1 and add it down here. So that's going to be 3 halves and 2/3, which is like 13/6 or something like that. 4, 9, 13/6. Do I agree with that? Now I can rescale this to 1. Right? And then I can use this to take this out, or in this echelon form. And so what's the solution to this? Well, I get x2 and x3 are 0. So my eigenvector looks something like this. Any multiple of 1, 0. The other two, I don't have real ones for. So let me leave you with this last question. This is what I asked. Everybody remember how we turn the plane 45 degrees? Only the 0 vector is a multiple of itself and not linear transformation, right? Because everything's twisted. There's nothing to stretch because you twisted everything. Now, can you turn a globe such that every vector on the, such that there is a non-zero vector on the globe that's a multiple of itself? Such that no non-zero vector is multiple of itself. It cannot be done because what you're looking for is eigenvectors. What does a linear transformation R3 look like? It's a 3 by 3 matrix. Everybody agree? When you try to figure out its eigenvectors, what can you say about the polynomial you're going to get? What degree is it going to be? Everybody agree it's going to be a degree 3 polynomial? Degree 3 polynomials always have a real root. Somebody tell me why?
Agree with negatives.
Complex roots have to occur in pairs. And so you always have to have at least one real root. That means you have to have at least one eigenvector or eigenvalue. So that means that you cannot turn that globe without keeping one of the vectors basically a multiple of where it is. That's not obvious, I don't think, right? Because I would think that I could, do this, mess around with the globe, but you can't do it. So, and the algebra tells you that. Okay, any questions? All right, well, you all have a good one, and we'll see you on Wednesday.